Okay, cool. I will mute and then you can unmute yourself. Okay, great. So welcome you all to this SAAO Colloquium. Today we have Javier Garcia. I think it's not Javier, right? It's Javier.
It's Javier.
Javier, wow.
Yeah.
Okay, great.
It's okay. I've been called worse.
Okay, so he is from, basically he's from Venezuela, and he did his Bachelor of Science and Master of Science from Venezuela only. And he did his PhD from Catholic University in Washington, and in close collaboration with the NASA Goddard Space Flight Center. And he did a number of postdocs in a number of institutes in USA, University of Maryland, and then Harvard Smithsonian Center for Astrophysics, and Carl Remis Sternwarte. Okay, and then he's working in Caltech as part of New Star team. So his main work is related to X-ray studies of black hole X-ray binaries. That's what, and ASIAN. That's what I am connected with him. And now I will not waste much of your time, and I will invite Javier to continue his colloquium. Thank you. Please share your screen. Thanks a lot for accepting our invitation.
Yeah, thank you so much, Neil. It's a very kind invitation. I'm happy that you give me the opportunity to talk to you guys. As I was saying before, I wish this could be in person. So next time when all this madness is over, please do ask me to come by, because I really want to go to visit South Africa. I like to, yeah. So I'm gonna be looking at the camera, but I have you guys on my other screen, and if people wants to open your cameras, that's fine with me. As I was saying, Sunil, if you have questions, just please feel free to interrupt me. It's hard for me to keep track of if there are questions on the chat. Sometimes people prefer to write them on the chat. That will be fine, but then most likely I will miss them during the talk while I'm talking. So if you want to interrupt me, feel free. If there is something you really don't understand and you need clarification, I'm happy with that. So yeah, today I want to give an overview of some of the research topics that I've been involved with, which really concentrate a lot around this technique called X-ray reflection spectroscopy. And I realized that I added in the title and timing, because we're now doing a bit more than just a spectroscopy. We also started to work more in timing analysis for accreting black holes. So this is something, obviously, I don't do it alone. There is, I've been very lucky to have good students and postdocs around me that have helped me with different parts of what I'm showing today. A lot of the results I'm showing today have been either produced by them or in a strong collaboration with them, and with a long list of really, really nice collaborators that I'm also very happy to have. And this is a likely incomplete list of them, but it's always nice to kind of keep in mind who are the people contributing to the results anybody's showing. And of course, funding is always welcome and needed. And my main funding agencies come from NASA and also from Germany through a senior fellowship that I still hold, and allows me to do visits to Germany, which is important because a lot of the models that we have produced are in a strong collaboration with the group in Bamberg. So the outline of the talk is more or less like this. I'll give an introduction especially for people that are not necessarily working on black holes or even on X-ray astrophysics, why black holes are important, how this field sort of started in Why do we do X-ray observations? And in particular, I'm going to be talking a lot about iron lines, iron K lines, K transitions, and I'll explain what that means and why they're so important for us. And in terms of the science we do, a very important part of it is providing estimates for the spin of the black hole. But we also have, around this, we have a lot of diagnostic tools to be able to recover other important physical parameters of the systems. So again, this is all very connected to the X-ray reflection spectroscopy technique. And I'll talk a lot about that. And as I mentioned a second ago, I'll talk about also the newer things that we're doing, which is a spectral-timing analysis. And I'll mention how, what are we looking into the future with the science. So in astronomy, X-ray astronomy is a fairly new field if you compare to, obviously the oldest field I will say in astronomy is in wavelengths is the optical, right? As long as humans have looked at the sky, they've seen in optical. And then you have other wavelengths coming in, and really X-ray astronomy started back in the 60s when Riccardo Giacconi started flying rockets with X-ray detectors. And there is a really nice story behind how this field started, and I don't have time to cover all that, but it's really interesting how a lot of things in science happen almost by coincidence. My understanding is that Riccardo Giacconi was really was interested in looking at the sky in X-rays. At the time, the only X-ray source known for sure was the sun. So they developed the first X-ray detectors. You need to fly them. You need to go above the atmosphere because the atmosphere is opaque to X-rays. So most of them will get absorbed. So and you can't really do X-ray observations from ground. So they did it with rockets. And think about we're talking about the 60s where the Cold War was at its peak. So it was perhaps a good time to propose experiments with rockets and things like that. Apparently, a lot of the funding came from the Defense Department in the United States because they convinced them that they could use these detectors to actually spy on the Russians and look for, whenever they were doing nuclear bomb tests, they said, well, there's a lot of X-rays and gamma rays releasing during those tests. So we could actually try to look down to Earth. But they really, he was an astronomer, so they really want to look at the sky. And the expectation was, in the very first experiment was to look at the X-ray reflection from the moon. The X-rays that come from the sun and reflect on the moon. So they pointed at the moon with these are very primitive detectors. Is essentially a Geiger counter mounted on a rocket. So really bad spatial resolution. Don't even think about doing a spectroscopy or anything like that. They're just counting X-rays. And the surprise was that they found, they saw the moon, but they also found a very strong source, much stronger than anything else. And it was coming from the constellation of Scorpio. So they call it Scorpio X1 for the first X-ray source detected. And actually that's, it's not a black hole, but it's a neutron star, an accreting neutron star. And I will say that's pretty much how X-ray astronomy was born. Almost at the same time, people were already thinking about how to find black holes, and there were already indications or ideas that X-ray could be the way because of the violent environment around it. So in a way, X-rays and black hole astronomy go almost hand to hand in history. So I'll fast forward several decades after, and in the 90s, I think was this another big boom in X-ray astronomy, because we start flying CCD detectors, which are much better. They have a spectroscopy capabilities with a decent resolution in energy. And they were more sensitive as well. So satellites like ROSAT and ASCA started doing, ROSAT was an all sky survey, so discovered a huge number of X-ray sources. And about that time was where there was a clear connection between the X-ray sources that were discovered and the position of known galaxies and AGNs. So that connection was very clear. A lot of the X-rays were coming from the centers of active galaxies. And also by the end of the 90s is when, based on ASCA observations, they started looking at emissions around 6 keV, where we know there is a strong transition of iron. So this is what I mentioned in the introduction, in the outline. This is called the iron K transition, or K alpha transition from the inner shells in the iron atoms. So this line in the laboratory is at 6.4 keV, and it was discovered in many of the sources that this emission was present. Very quickly, very smart people realized that you need a lot of material to reprocess X-rays to produce this line. So they start thinking about reprocessing of X-rays in a very dense and optically thick medium. So they start thinking about the accretion that is around the center. And of course, they already knew that there was indication that there had to be supermassive black holes in the center of many of these galaxies. So this idea of an accretion disk forming around a black hole and reprocessing X-rays was already sort of forming back then. And one of the seminal papers in the field is, it has to do with the ASCA observation of this one AGN called MCG-63015, where they were able to clearly see the iron K line, where you see in the lower panel here in the red points is the data. The interesting aspect of this emission is it was not symmetric. As you can see, is asymmetric and skewed towards the red. And this was explained by assuming that if the emission, if the reprocessing of X-rays and then the line emission occurs near the black hole, is going to be affected by relativistic effects. And those effects will change and distort the shape of the line. And in fact, the blue line here is a primitive model that includes some of these effects. And you can see that it actually does a very good job in producing this. So this was sort of a revelation. We now have indications of emission close to a black hole affected by strong gravity. So the way this works is, if you think about the emission coming from a disk, a thin disk, geometrically thin, you can think about the emission coming from one particular orbit. If you have something like a delta function, a one given energy as shown in the little animation on the right, you just with classical physics, you have that rocketing of the line in energy to the right and to the left, because you have material that is approaching to you, and you have material that is going away from you in a disk. So the blue side, it means it's blue shift, that is material coming towards the observer. The red side is red shift, there is material going away from the observer. And this produces what some people call a double horn profile. And this is seen in many other cases in other wavelengths as well. So this is well understood. And this is all, let's say, Newtonian physics. However, if you're close to a massive object and spatial relativity, what it will do, it will beam some of the radiation. The part that is coming towards the observer gets enhanced, while the part that goes away gets weakened. So this double horn now becomes asymmetric in intensity. So you have the blue side becoming more intense than the red side. And then on top of that, you have a general relativity effects that will produce gravitational redshift of the entire profile. So if you combine all these things together, you get the final line profile, which is shown at the bottom. This is a simplistic cartoon of all the effects for a single line, a single delta function. And what is important of this is that this will depend on the position where the emission occurs, but that position will also depend on the spin of the black hole. And here, maybe going faster, but immediately I'm showing what the line profiles are for a Schwarzschild black hole, which is a black hole described by the Schwarzschild metric, meaning it has no spin. And the same line profile described by a Kerr metric, it means a black hole that is spinning really fast. So they produce different line profile. And the reason for this is because there is a connection between how close an accretion disk can sustain orbits to the black hole and the spin of the black hole. Because of frame dragging effects of the space-time, or let me just start saying, in an accretion disk around a black hole, the inner edge of the accretion disk cannot go all the way to the horizon. What happens is there is a point in which particles cannot sustain circular orbits anymore. They cannot do Keplerian orbits around the center. They will just plunge directly to the black hole. And this occurs at a particular radius that is larger than the horizon of the black hole. So we consider this to be the edge of what we call the accretion disk. It's not that there is no vacuum inside, there is material, but the material is essentially falling directly to the black hole, sort of like a waterfall, right? So all the features that we see, they're produced in the actual disk, in the accretion disk, because you need the proper condition. You need the gas to be optically thick, you need to be in orbit, so you need a proper accretion disk. So this inner edge is the last place where you can produce observable features that we see in the spectrum, right? And as I start saying, the radius will depend on the spin of the black hole because of frame dragging effects and general relativity. So in the middle here, in the cartoon that I'm showing here, in the middle is a black hole that is not rotating. And then this inner edge sits at a particular radius that happens to be 6 times the gravitational radius, gm over c squared. And this produces certain amount of distortion. If the black hole is spinning really fast at the maximum spin, actually what happens is that it allows for that circular orbit to be sustained much closer to the black hole. Because it's much closer, of course, it feels stronger gravity. Therefore, the gravitational distortion that you observe in the spectrum is going to be larger. The opposite case is the one at the top, in which the black hole is spinning at maximum spin, but in an opposite direction, retrograde to the direction of the orbiting infalling gas. In that case, the actual inner radius sits much farther away, and therefore the effects of the gravitational distortion are at the minimum. So from this cartoon, you can quickly identify the fact that we have a diagnostic tool here, a very strong one, which means if you can model this distortion accurately, then you have a way to understand how close the accretion disk is to the black hole. And because that is a function of the spin, you can actually derive the spin. That's what we do with these sort of models. I will explain this in more details in a minute. But before I do that, I just want to mention that this is an actually very powerful tool for many reasons. And one of the central ones is that this is, in a way, independent of the mass. Or another way to say it is you can apply the same technique to any accreting compact object that emits X-rays and have an accretion disk. So you can see these effects in neutron stars, in stellar mass black holes like those in binaries, or in supermassive black holes in the centers of galaxies. So we're covering a very wide range of masses, essentially any black hole or neutron star that has an accretion disk, has the capabilities to produce this signal, and we have therefore the capabilities to model it with the same sort of technique. In the case specifically about black hole spins, why is this so important? Well, there is a simple reason, which is black holes are either extremely difficult or extremely simple objects, depends how you see them. They're actually very simple objects as physical objects, because there is not much you have to describe them. A black hole is entirely described by its mass and its spin. In general, you have the charge as well, but in astrophysics, the charge gets neutralized very fast. So in practice, for an astrophysical black hole, you only need to know its mass and its spin, and you have completely defined the black hole. So, so immediately you can see, well, if you can measure spin, you're halfway through to describe any given black hole that you have. More deeply, spins are central because they describe, they give you some sort of access to the history of the black holes. And in particular for supermassive black holes, for example, the distributions of spins versus mass, or the distribution of spins in the local universe, they will give you information about how these black holes were formed and how did they evolve. People that work on supermassive black hole evolution models, they will predict different sort of distributions of spins according to how they evolve through time. So for example, if the black hole acquire mass through a steady growth, a steady accretion, they will have a particular distribution, which is different than if they were formed through many mergers. And how these mergers occur, whether they are completely chaotic and random or whether they are hierarchical, they also end up with giving you different solutions. So if you, this has a very high relevance to this field, in the sense that if we can observationally constrain what's the distribution of black hole spins, then we're gonna start saying something about which of these models are right and which of these can be wrong. And this is coming from a compilation done by Chris Reynolds very recently that shows sort of the current state of where we are with the measurement of the spins for supermassive black holes. It's not very pretty. You see some error bars are quite large. I think all the red points are essentially limits. They're not properly constrained. But we started building a sample that gives some information about what the distribution might be. In the case of black hole binaries, when I talk about black hole binaries here, we're not talking about two black holes. I'm talking about the black hole with a stellar companion. These are typically, we see them in our galaxy, in the Milky Way, but of course they exist everywhere else. And the situation is very similar. You have a black hole accreting mass from a companion star forming an accretion disk. So again, we can apply the same technique. What I'm showing here is the current, maybe not so current anymore, but the distribution of the spins for these stellar mass black holes for all the known sources. In this case, I'm actually showing, this is coming from a paper by, this is a compilation done by John Tomczyk and was published in a Strobeck's paper by Ray et al. In 2019. But anyway, the different colors show different techniques, not only reflection, but reflection is, as you can see, the most popular is shown in blue, and there is some sort of distributions of spins going from 0 to the maximum. And this is the relevance of spins for stellar mass black holes is similar to the supermassive ones. It's not clear yet how stellar mass black holes acquire their angular momentum. If you see a black hole, a stellar mass black hole spinning at close to maximum, you ask the question, well, how this happened? And the black hole was formed after the collapse of a star. Was this angular momentum already in the system and just was preserved? It was given after the explosion. There was some kick. or it acquired the spin through over time. And whichever version of whichever answer you try to take, each one has their different problems. So in general, understanding what are the spins for the sources that we're currently studying is a big thing. Now we have measurements done through gravitational waves detections with LIGO. And one important aspect that I'm particularly very interested and puzzled about is the fact that in the case of LIGO sources, and these are indeed two black holes in a binary system that merge into a single one, the spins that are coming, the final spin for the final object that is measured by LIGO, seems to be concentrated always around 0. And this is in discrepancy with most of the spins that we measure for similar black holes. So this is opening new questions. Is it because somebody is doing something wrong, or is it where we've seen different populations? I don't think we understand this yet. I also want to caution that the fact that we have this sort of powerful technique to measure spins is not always a great thing. It's a relatively easy model to use. If you have an X-ray observation, you can get the model and feed your data, and typically it will work fairly well. But there are many different systematics and correlations among parameters that need to be taken care of with some caution. And I like this. The case of Cygnus X1 is a very famous stellar mass black hole. And I just took a few of the spin measurements done with reflection spectroscopy over the years. And if you plot it over time, it almost looks like if Cygnus X1 will be spinning up. And this is of course not real. This is not a physical thing. It's not you cannot expect the spin of a black hole to increase this much in this short amount of time. What is happening here is that the data is getting better, and hopefully the models and the observers are also better in converging to a value that is more accurate. So I'd like to say a few words about the X-ray reflection spectroscopy technique that I've been mentioning so much. And this is a cartoon to describe the general overview picture that we have of what happens in these systems. In this case, you have this beautiful artistic rendition of a star being giving some of its material through to a companion to the black hole, and which is forming an accretion disk around it. And there is in the radio we see typically jet emission, so the artist decided to put the jet here. In pretty much in any of these sources, we see what we call coronal emission. This is, you can call it non-thermal emission as well, is typically a power law continuum that dominates the X-ray spectrum, which is shown in blue here. This coronal emission, we can talk a lot about what this might be. Some people think it's a base of the jet, or some just hot gas around the center. In any case, some of it will go directly to the observer, and you see it as a power law continuum. But another fraction will go to, will shine into the accretion disk. Now, those X-rays will interact with the material. They get reprocessed. We call it reflection, but that's actually a bad name. There's no actual reflection as in a mirror. It's reprocessing of X-rays. Some photons will get scattered back. Some others will be absorbed and re-emitted at different energies. So there's a lot of things going on to the radiation that goes into the material. Sorry. What happens is that this reprocessing changes the power law to a spectrum that has complicated structure. It has emission lines, it has absorption, it has a whole bunch of spectral features. And typically it should look more or less like the green line here. What you're seeing here is not one, but two iron K lines, the K alpha and K beta transitions, which are very strong in the most neutral ions. There is this feature here that looks like a very sharp thing. It's an absorption edge for the K shell, that's the innermost shell in the atom. And there is this big round thing, which is produced by electron scattering. We refer to it as a Compton hum because it's done through scattering of photons in the hot part of the disk. So this is what I would refer to it as distant reflection, because it's reflection that occurs far away, far enough such as it's not affected by the gravitational potential of the black hole. If the reflection, however, occurs relatively close, then it will be affected by gravity in the ways that I described earlier, and this will tend to blur and distort the spectrum. In this case, it's an actually very, very strong blurring. As you can see, the green line becomes the red one that looks like it has almost no features. It does have some features, but they have been smeared out by all these effects. When you put all this together, then you can provide a very good feed to the observational data, which is actually real data for a system called GX339-4 shown here. This is data taken with NuSTAR and Swift observatories. So reflection, the modeling of reflection has been around for quite some time. Back in, as I mentioned, in the 90s were the first detections of iron K lines. So people start working on trying to model the same. I don't have time to go over the details, but if anybody's interested, please ask me later. I would just mention that, earlier models were just looking at neutral iron lines with some Compton scattering. Then later on, it was realized that, well, astrophysical objects have more than iron. They have other, the presence of other elements, and each element will have its own X-ray lines, and they should be included in the models as well. But this is all neutral. This is all assuming neutral species and no ionization whatsoever. It was later done by Randy Ross and Andy Fabian. They developed the first proper models that included ionization effects, meaning the state of the gas is not always the same. It depends, among many things, it depends on the strength of the X-ray field that is illuminating the gas. So if the field is weak, you get mostly neutral lines. But if the field is strong, you're going to get more ionized, and then you get other species, other lines to be involved in the mission. What I've done for quite some time now is improving on these models, because I started my career as an atomic physicist doing atomic calculations for different elements. And these are all the things that we need to include in the models to properly describe what happens to the microphysics in a photoionized gas. So we now have built a large library of atomic parameters for not only iron, but pretty much any other element that is important in astrophysics, to try to describe all the complexity of the line emission and the production of different spectral features. Maybe here I'm going too much detail, but this is just a quick way to show the number of transitions involved in a typical calculation just for iron K. So this is a tiny region where we see these lines between 6 and 7.4 kV. The group on the left are all the K alpha transitions for iron, for different species of iron, going from the bottom is neutral all the way to the top. You're going to the mostly ionized ions. That means you're removing electrons. You go to iron 26, which is you have removed 25 electrons, meaning you have only one left. And this is a hydrogen-like species. The group on the right is the K beta transitions. So K alpha is the transitions between the second, n equals 2 level to the ground. The K alpha, the K beta will be the n equals 3 to the ground. Never mind all the crazy details. The point is all these transitions are potentially involved in a given calculation, because in a photoionized gas, you don't have only one ionization, you have a range of ionizations, and at different depths, lines from different elements will be produced. And what this shows is that these lines actually shift in energy. They're not always a 6.4, as it was assumed at the beginning. They shift to 6.7, and then even to 6.9 for the most ionized things. The K beta transition doesn't always occur. It occurs at a certain point, and then it's not there anymore. So if you produce models with all this data and you change the conditions, for example, you change the amount of flux, keeping the density constants, you will see that shift. You will see that the K alpha and K beta transitions are there at the beginning, but as you increase the flux, then the spectral profile changes quite a bit. It shifts to higher energies, and at some point it gets so highly ionized that only a couple of small transitions are left. So this is all important. This is all, it's gonna matter at the moment of modeling these observations. And this is just a blow up of everything, right? This is a very high resolution model with a resolution typical of microcalorimeters. These are the new instruments that we're hoping to have in orbit very soon that will provide a big leap in a spectral resolution. So this is what we need now. We need very detailed microphysics because the data is going to get perhaps too good for what we have currently in our models. So this is one of the things that we're looking for the near future. As an example, I show a comparison, sort of one-to-one of our models with the previous generation, which is called Refly on X, produced, as I said before, by Ross and Fabian. And you see that, I mean, this is an unfair comparison because back at the time, the resolution needed was much lower. So of course, it looks ugly. It looks lower resolution because it is lower resolution. But the big point here is that they only included the most important lines. There's a lot of physics and a lot of smaller transitions that are missing from the previous databases. And they're all going to contribute to the overall profile that you see, even if you will do it at low resolution. I think I'm taking too long and I want to get into actual results. So I'm going to go a little bit fast here. In terms of observations, the past, present, and future of X-ray detectors, I just wanted to show how things look. This is work we did with a now decommissioned X-ray satellite called RXTE with a resolution of 1 kV at 6 kV. So this is fairly poor resolution, yet you get to see the iron line profile has been smeared by relativistic effects, the absorption edge, and this content hump here that I mentioned before. Now we have NuSTAR, which NuSTAR is an X-ray satellite that for the first time is capable of focusing X-rays at high energies. So this allows to have better sensitivity, lower background, and it has a pretty good resolution. So this resolution is a factor of 5 better than before. So you see we can get a similar, this is the same object, seeing a much better resolution with NuSTAR. And in the future, we expect to have microcalorimeters with, there will be a factor of 10 better in resolution or more. And this will provide just an unprecedented amount of detail in every spectrum we take. So our model, the one that we have built, including all these microphysics, all these atomic physics that I described, it also includes all the relativistic effects. So what we've done is to put everything into a single package, such as the users can have access to all the physics at once. The model that does just the reflection is called Silver. The full package is called RelSil, which includes all the relativistic effects. So that means that with this model, you can try to constrain the different parameters of the system, such as the black hole spin, the inner edge of the disk, the inclination of the system, and many other things that have to do with that non-thermal emission component that I mentioned before. Just to give a quick taste of how the models behave with different parameters. Here you have some of the important ones. So black hole spin, the higher the spin, as I mentioned, it will tend to make features broader and smear things out a little bit more. The corona height refers to the height of the non-thermal emission. We have a model that is a toy model in a way, but it allows us to have some geometry in the system. So we put, it's called a lamppost model because you assume all the emission comes from a point source in the axis. And depending on whether that point emission is very far or very close, it will produce a different reflection spectrum as well. The inclination has an effect because you get to pick up more GR or special relativity effects depending on the inclination in which you see the disk. So very high inclination, you're gonna see a lot of general relativity effects. And you can see how the entire profile shifts to the blue at high inclination because of this. And of course, the iron abundance is a central parameter because it controls how much iron we put into a model. Of course, that will increase not only the amount of emission from iron, but it will increase the amount of absorption. So it has a kind of weird way to affect the models. This is what is called the hardness intensity diagram for a black hole binary. That is, we call it the prototypical binary because it does everything that you want binary system to do. It's called GX339-4, and it's a black hole with a companion, with a stellar companion. And this is all data taken with the RXT telescope over probably 16 years of its lifetime. So every point here is essentially, is almost a daily observation. Through these sources undergo what we call outbursts. If you look at them in X-rays, they typically don't do much, they're in quiescence, but suddenly every once in a while they will erupt, almost like a volcano. Become very, very bright in X-rays for a while, and then they'll die after, it could be weeks, it could be months. And the recurrence with which this happens is not the same for every object. So in this case, GX is a very active, it does outbursts every 2 to 3 years. So we've been able to track this evolution through an outburst many times. And what happens is, in this diagram, we're showing the X-ray hardness. In a way, you can see it just like the slope of the spectrum. And in the y-axis is the intensity, is how bright it is. So you can see at the start of the outburst, it just gets really bright while more or less preserving the slope. And this is a particular state we call the hard state because the X-ray spectra is dominated by hard X-ray emission. This means mostly looks like a power law with a lot of reflection features on it. So if you look at the spectrum, it's going to be a power law typically with a slope gamma 1.6 or photon index 1.6, if that means something to you, or at least below 2. At some point, the luminosity sort of stays more or less constant, but there is a big change. You can see it's very fast in time. There is a big change in the slope of the spectrum. And that is because it becomes more thermally dominated. And we refer to this as the soft state because most of the emission is in the soft part of the X-ray spectrum. So what this means is that the disk, the accretion disk, becomes much more luminous. So what you get to see is something that looks like a black body. It's an actually multi-temperature black body emission because you have many different annuli from the disk emitting. But you will still get to see some reflection features. There's a lot of phenomenology here that I'm not going to cover, but it's extremely exciting and interesting to understand the properties of these systems. Something we did, it's been a while now, back in 2015, is to take these one black holes, and we figure there is so much data. Although this is low resolution, sort of limited instruments, this particular observatory took so much data over the time for this source that we figured there's something that we should be able to do with it in terms of details of reflection. So we took all the observations in the higher state, defined some regions like I showed here, some boxes, and combine the data within the boxes in a particular way to maximize the signal. And in fact, when you remove the continuum from these observations, we define six regions. So you have one spectrum for each one of them. We get to see very clear signatures of reflection, as I showed before. And these are different luminosities of the source while it was in the higher state. So something you can do with this is start looking for trends and evolution. So first of all, with the reflection model, of course, we were able to measure the spin. It has been measured before for this source, so we confirm it's a highly spinning black hole. It has a particular inclination and very high iron abundance. And this is something, if I have time, I'll mention it towards the end. But again, something you can do is to look how these sources evolve through this outburst. And what we were able to detect is that the inner edge of the accretion disk is moving inwards as the source evolves. As it becomes more luminous, the inner edge is moving from a few times RG towards the closest possible place that it can be. At the same time, the coronal emission seems to be doing something as well. The power law has a cutoff of high energies that we relate to the temperature of the corona. So it actually looks as if the corona was cooling down as it becomes more luminous. And this sort of makes sense. If you have a hot plasma producing more and more photons, it takes away this energy, so it's cooling down. So this, at the very least, shows that there is a close relationship between the disk and the coronal emission. So this is because it's a prototypical black hole, is a source that has a lot of interest, and it has a lot of observations. A lot of paper has been written on it. So here I'm compiling all the different measurements for the inner radius using reflection spectroscopy for the source. Different colors are related to different instruments. But when you put all this together, it tells you pretty much the same story. It shows you that the inner radius is evolving from being a very truncated disk at the beginning of the outburst, which is the part where you don't get to see many X-rays. Suddenly, when the outburst starts, it means the disk is filling in. There is an increasing accretion rate in the system, and material is being dumped towards the black hole, and it's forming an accretion disk that becomes more and more luminous. And then you get to see that with this technique, because we're able to measure the inner edge of the disk, we can see how this is moving inwards as the source evolves. We've done this with many sources. I'll go briefly through some of the important results. I think the ones that excite me, this source is called MAXI J1820+070. It's another well-studied system that has inclination, the inclination of the orbital, the binary orbit, have been measured very well. We did a study with one of my postdocs, Riley Connors, and we took the best data that we have for this source with our XTE and ASCA, I think, covering a broadband spectrum in X-ray. You can see goes from 1 kV all the above 100 kV. And we fit it with all the best reflection models that we had. There's a lot of details here that I won't mention. The point is, everything worked out great. The only problem was that no matter what we did, the inclination required by reflection was around 40 degrees, while the inclination measured for the orbit is more like 75 degrees. So this is a big discrepancy in the inclination. Typically, when people see this sort of discrepancies, they will talk about warp disk, which is this idea of if the angular momentum of the black hole is misaligned with the binary orbit for whatever reason, they don't necessarily have to always be aligned. If that happens, then the inner part of the accretion flow, so the most inner part of the accretion disk, will tend to be aligned with that angular momentum of the black hole, while the outer part of the disk will try to be aligned rather with the inclination of the orbit of the binary system. So that can create a warp. So a disk that has one part of it is at one inclination, and the other part is a different inclination. That sort of would explain this, since we expect most of the reflection to come from the inner part. So you could say, well, the inner part is producing reflection at a different inclination. The problem is it's a very large discrepancy. It would mean a very large warp in the disk. The other problem is there are very good measurements of the jet emission seen in the radio. It's aligned with the orbit. So the inclination measure for the jet is agreeing with that 70-something degrees of the orbital inclination. So this is kind of like complicated, because suddenly you have to think in a system that has the spin is misaligned with the orbit, while the jet is aligned with the orbit. So jet and spin are misaligned, which is a little bit weird. And then you have a warp disk. So this is complicated, and I think it'll be hard to explain. So one alternative explanation that we're trying to figure out is possible obscuration of the disk. If you look at the what is called ray tracing simulations, these are simulations in which you follow the trajectory of individual photons in a curved space-time. This is what we have to do to produce these models. If you assume that the actual inclination that is measured is correct, that the binary is correct, it's a very high inclination, 70-something degrees, it is likely that the disk will produce some obscuration of the central region. So the disk is blocking itself. The outer part blocks the view of the inner part. And this is what is modeled here. When that occurs, what happens is you tend to block predominantly the blue side of the line, of the iron line. And this produces an effect that is similar to what you would see at a lower inclination. So the hypothesis here is likely that what's happening is if there is obscuration of the central region, we are seeing a line as if would be produced by a disk at a different inclination than what it really has. We don't have the models that does this effect self-consistently, but we're working on it. And so the idea is to include this effect and see if the disk has some scale height, if it has some thickness, can we actually predict the right amount of obscuration to account for this difference in inclination. Another really cool thing that we found very recently, working with the same source, J1820+070, when we look at observations in the soft states or softer states where you have this very strong disk emission coming in, we couldn't fit the spectrum with the standard reflection models. None of the things that we tried worked. And the problem was always there is a clear emission, there is a clear iron line emission as we typically see in reflection. There is no Compton hump. If you try to fit this with a standard reflection model, the model comes with line and with that broad feature that I mentioned before, the Compton hump. So that will destroy the fit at high energies essentially. So the model that worked is a model that was actually developed for neutron stars, in which the illumination is not assumed to be a power law, but rather a black body. So a black body illumination will produce a black body-like reflection spectrum that has the iron line, but has almost no Compton hump. And this worked actually tremendously well. So the only way to explain this is not that we think this guy is a neutron star, because we know the mass very well. It is a black hole. What we think is happening here is an effect called returning radiation, which is when you have a disk that is very luminous, you're going to have some part of the radiation going to the observer. Some other photons, if they are produced close to the black hole, so they will actually go into the black hole. Obviously you don't get to see them, but some of them will circle around and they will go back to the disk again. That's why it's called returning radiation. The disk is illuminating itself. So in this state, we actually don't get to see much of the power law emission. That corona emission is almost gone. So who is producing these reflection features? The best explanation we have is the thermal emission going back to the disk and producing a different type of illumination that produces on reflection. And this is actually an effect that has been predicted decades ago. In the 70s, Cunningham wrote a beautiful paper where he developed all the equations, and they show that there is some fraction of this emission that has to go back to the disk. We didn't talk about reflection, but the principle is there. So we're now producing models in which we do the proper ray tracing to show that this is in fact what's happening. It's not the standard reflection, it's just returning radiation producing a different sort of reprocessing emission. and in fact, we get to see this in other sources, like again, GX339. If we go back and look in the soft state, we see that the standard models don't work. Actually, returning radiation alone doesn't work. In this case, you need both, because you have both a strong thermal emission, but you also still have a power law emission there. So in this case, you have reflection being produced likely by the two components. I think I'm going over my time now. Let me just mention that we're now evolving models to include the timing aspect. Photons. Sorry, is that a question?
No, please go ahead.
Okay, sorry. None of these things that we phenomena that we see are static. They're vary in time, and variability is important in X-rays because it will produce particular signals. You can just think about it as echoes in X-rays. So in many cases we get to see lags between different bands, and some of these lags are caused by something that is referred to as reverberation. And you essentially use, if you have the coronal emission has some intrinsic variability, it will take some time for the photons to travel from the corona to the disk, produce a reflection, and that reflection to go to the observer. So that difference in time can be measured, and it produces a particular distinct feature. So being able to model now this in time, it opens a new dimension to the whole thing. And unfortunately, I really don't have the time to go over. There's so many details, but this is a very recent work done by one of our students, Jingyi Wang, and my postdoc, Gulo Mastroserio, who developed one of the authors of this new spectral timing model. The model is called RelTrans and is available for anybody that might be interested. This model is capable of modeling not just the spectrum, as what I talk all this time, but it can also model these lags in time that I'm describing. So we look at this relatively new source called MAXI J1820. It's another binary system in our galaxy that was discovered just a few years ago, and it became one of the brightest X-ray sources in the sky at the time. So it has provided a huge amount of beautiful data. Sorry. And by modeling not only the spectrum, but the timing properties, we were able to see correlation of what happens to this coronal X-ray emitter and the jet. If you look here in this slightly busy plot, what you're seeing here in red, you see the flux in radio measured for the jet through the evolution in the hours of this source. So it's going from the hard to the soft state. And what you get to see here is there is a steady jet emission, and suddenly the jet is quenched, it goes down, and then there is some sort of like a burp or something, maybe there is a ballistic emission of material at the end. We are able obviously to measure the X-rays, and you see the X-rays also go down sometime after the radio jet is quenched. The interesting thing is, with these complicated models of reflection and timing analysis, we're able to put constraints on the height of the corona. How far is the primary emission from the black hole? And we measure this in RGs with some gravitational radii. And we can actually do the same thing. We can measure through the same evolution, through the same hours. And what we're seeing is very clearly the height of the corona is increasing at the same time that all these things are happening. So it looks like the corona is sort of expanding and maybe releasing most of its material, because at the point where the radio emission is quenched, you get to see this rapid increase in the coronal height as measured by our models. So I'm still trying to understand exactly what this means. I don't think we have a clear, detailed interpretation of what's happening, but this is very telling that there is a very strong connection of all these processes. So reflection is just a great diagnostic tool. You can have access to the structure and geometry of the accretion disk, and then by connection to some of the properties of the black hole. I don't want to say much more now. I had a whole section about microphysics and how we're pushing the models to higher densities, and there are interesting atomic effects there, but I really don't have much time to go into this. If you're interested, please just ask me at the end. I just want to say that this seems to be connected to the iron abundance. One interesting aspect is when you look at most of the reflection measurements, they all want to have very high iron abundance. And when I say high, I'm talking about several times. The peak is at 5 times solar. Some cases go 10, 12, crazy numbers. This, I don't think these are real abundances. I think this is something, some other effects are taking over, and the model, the way the model can account for them is to increase the iron abundance. So this is a very active problem right now, where we think it's connected to the density of the accretion disk. Again, if you're interested, just ask me. And I also think this high density plasma effects will have other repercussions in sort of, for example, models for winds, because what I started learning is that plasma effects at high density, they occur at densities that are not so high. There are differences in the models that might affect the way, for example, people that model these winds are doing what they're doing. So again, this is all very preliminary, but if you're somewhat interested, just let me know. And of course, this is going to be very important for the new generation of detectors that include these very high resolution instruments. In the not very future, actually, very soon we'll have also instruments that are capable of measuring polarization. So we're already working actively on including polarization into the reflection models. This is a whole different story, because now you have to solve, obviously, different components for different stock parameters. And now you don't have only one solution, you have several solutions that give you the properties of the polarized emission. So it's a demanding theoretical work, but I think it's going to be very important once we'll start getting data for these sources that measure polarization in X-rays. So I'll just stop here. I'm sorry I went so long. I really wanted to give you a good overview of the many, what I think are very interesting different results that our group is producing, and hopefully convince you that there is a bright future for X-ray and for black hole astrophysics, because we'll have a new generation of very powerful detectors. And the good thing is we'll have excellent data. The bad thing is that certainly every model is going to be wrong. So we need to be prepared for that. And that's what we're working hard to make sure things are at the level of the data that is going to come very soon. I'll stop here and take any of your questions. Thank you.
Thanks a lot. It was really very nice journey through many stages of X-ray reflection spectroscopy. And definitely we are we are waiting for GRISM to change the reflection and understanding of reflection in low energy band.
Yeah. Definitely.
So now we are open for questions. Please ask or raise hand, and you can unmute yourself and ask questions to Javier. Please. Okay. Okay. No problem. Sazrin said like it's a super talk. She has to run. Anyway.
Okay, thank you.
Anyway, I was interested to know how you will be including polarization in your models. So
yeah. So what I wrote here is the simplest version of the transfer radiative transfer equation, which is really what we need to solve in any kind of reflection model. I can go into the details, but I don't think it matters too much. This is just the equation we need to solve, and this is for the intensity of the radiation, right? Mm-hmm. As it goes into a media with some optical depth and some angle, and the S is the source function that contains all the atomic physics part. When you go to polarization, what this means is now you have the in general, you have the 4 stock parameters
Yeah.
that have different components of the field. What we plan to do is the simplest version, which is you assume as azimuthal symmetry, then the U parameter is 0. And if we ignore circular polarization, which we think is a fairly good approximation, so only linear polarization, then the V parameter is also 0. In this case, then you only have the intensity and the Q parameter. So this means having to solve now 2 equations. So you're going to have an equation for I, and you're going to have a similar equation for Q, and they are connected through what is called a redistribution matrix. This has to do with the photons that are scattered through electron scattering, right? So there's a complicated matrix of how this is implemented, but the simplest sense is we have to solve now, instead of 1, 2 transfer equations that are somewhat coupled. The final solution, then you're going to have, instead of just I, you have I and Q. And with these 2, then you can construct what's the degree of polarization and what is the angle of polarization as well. And finally, the idea is, so that's just for the reflection, but then what I'm showing here, which is the pretty figure, is not mine, it's from Henry Krasinski, where what they're doing is including polarization in the ray tracing part. So the part of the calculation that does what happens now to the reflected photons in GR, right? So that also includes polarization. So if we have the polarization in the intrinsic reflection, now we can connect it to the ray tracing and have the full model that says, okay, this is what the observer should see in X-rays.
Okay, won't this have kind of degeneration parameter space?
Say that again, the what?
So won't it trigger multiple degeneracies in the parameter space? Like you will have less number of observables and more number of parameters in your model?
Well, it depends what are you going to model, right? So my understanding is the IXPE, so the mission this mission is almost ready to be launched. It should have happened already, but I think it's going to be launched by the end of the year. The data that will be provided will be essentially what you get to see is degree of polarization and angle of polarization per energies in a range of energies in X-rays.
Okay.
So that's what we want to model. So how you model this, okay, our models are complicated, but at the end of the day, you might, for example, you might go and say, I have observations of SIGX1 with NuSTAR. With that, I can model the reflection, and I can constrain a whole bunch of the parameters that go into the model. And what is left is to make sure that this I and Q correctly represent the degree of polarization that is measured by IXP for the same parameters, right? So I guess the question is, we'll see what happens, right? In terms of modeling, that sounds very simple because you just need to measure those 2 things, those 2 quantities per energy. But whether the two products will agree in the rest of the parameters, that has to be seen. Yeah.
It's like back and forth matching, cross matching between 2 set of things.
Yeah, that's what I have in mind right now. It might end up happening differently, but I think that's the best we can do. It's not going to be fantastic data. I mean, we're talking about, I think they cover between 2 and 10 kV, and it's just going to be, these are difficult measurements of polarization, right?
Yeah.
So I think you might be right in saying maybe we're not going to be able to constrain a lot, but these are the first steps, right?
Yeah. Actually, yesterday I was attending one talk by Henrik, and he mentioned about IXP and also XL caliber.
Yeah.
This balloon-based experiment.
Yeah, exactly.
Yeah.
So Excalibur, it uses detectors that are very similar to the ones in NuSTAR. So I guess it's still in the phase of demonstrating the technology through a smaller version. So that's what they do, balloon detectors. And I think if they're successful with that, then that will give them perhaps the I don't know, the authority to go and propose for a bigger mission. Say, okay, these are the detectors we want to put into a spacecraft now.
Okay.
Yeah.
Okay, great. Thank you. It was a really nice talk, and unfortunately, it did not. I mean, not many of our colleagues could attend due to the conference I mentioned, this conference which is going on. Anyway, this will be uploaded on our web, and we may have some questions on YouTube by the people.
Oh, of course, my email is at the beginning, so
yeah,
well, people can just send me an email. I'm happy to talk to anybody that is interested in these models.
Yeah. Okay, great. Thank you. Bye.
Thank you so much. Take care.